the stream died. I don't know why. The stream failed a little bit. Maybe I had a disconnection. I apologize for the abrupt ending if you were viewing it. Let me check. Okay, actually it was a good idea. Maybe it was a blessing in disguise that the stream died, because I was talking about irrelevant things like the cards that I got. Recently, and yeah, I suspect people are not interested. Don't know. So anyway, let's just start over. Welcome to the stream. I'm reading this paper called Delayed-Rejection HMC with for multi-scale distributions. Hey, you're interested? Oh, about the cards. So this is, I don't know if this is actually captured in the previous stream, but this is the pink Jasper's deck. It's called the Favorite Day Edition 2, and I got the pink one. Really happy about it. Feels nice. Sounds really nice as well. Don't know if it captures well on my my mic, but feels sturdy. Really snappy cards. I also got the Neon Knights, which is really interesting, bold design. The color looks really cute. Yes, the chat is super delayed. I think that's the thing. Yeah, I don't know what I can do about it, but yeah. But the card design is a bit ridiculous. You can't obviously use it for anything else, because this color just looks crazy. Under bright light you can't see anything. You see, yeah. I can't. Let me see if I can do a reverse span. Left-handed, pretty horrible at that. Okay. Yeah, and I was complaining about this purple deck that is disappointing. The people at Touch, why you use cardboard? So like I said, this deck opens sideways, which is arguably the coolest feature of the entire product, right? Or how it works is that, you know, this card box is moving like this, so when it moves tilt upwards, this bottom part pushes the cards up. So that's really cool. Cards come out like this. Right, the cards themselves, nice color. I mean, in person it looks a little worse than in pictures actually, because you have this weird patch here, which this yeah, I mean this part that looks, wait, how do I even point it? Yeah, this part looks kind of weird. It says derive, but with the E with the thing, so it's, I don't know, French. The deck is okay. Not the biggest fan of the stock or the feel, but it's fine, right? It's subjective. But what I have a problem with the box, really cool design, but really bad quality on everything. Super cardboardy. There's nothing. It's not even a bit waterproof like any deck. Like, you know, the basic deck where they have like some coating. This does not have that. Very disappointing. And most decks I leave the cellophane on to protect the box, kind of keep it clean and dry. But this, you can't do that because you got to open it, and the fact that you can't use cellophane or you have to remove it means that the deck should at least be protective against like weathering, right? And this deck, I mean, I had it only just for like 1 or 2 days. I didn't use it much at all, and already you can see like the cardboard is starting to fray. Like if I put this in my pocket and I go out for a day, it's gonna be gone, right? It's gonna be pretty beat up. So not super happy with this deck, but you know, it's cool design. Okay, let's go on. Yes, so we're reading this paper, and I'm only a few pages through before I was sidelined into reading 2 other papers. But those 2 other papers are important as well. So they are the extra chance the extra chance generalized HMC as well as the HMC without detailed balance, and they are the same algorithm, right? This paper explains the same concept in a slightly different way, which has some implication that I don't fully appreciate at the moment. It says that, so this method says that you do the extra chance stuff, you delay rejection, but you give up on detailed balance, right? But you don't spoil stationarity. You achieve stationarity by fulfilling the fixed point equation of your Markov chain. Here it says that you can get detailed balance, so it's saying that it is explaining something that this paper isn't. Yeah. So these two papers are actually very important that I read them, and I finally have, more or less. And if I need more details, I can always come back. But I hope I get the right main idea. Okay, so now let's continue here. Okay. Yep. The DRH, yeah. Smallest step. I thought there's a famous paper that wrote about this. It's called DRAM, Delayed Rejection Adaptive Metropolis, something like that. By Hario, right? Yeah. Yeah, this one. Oops. One thing I realized about this research area is that, you know, you see a lot of fancy samplers and fancy methods. You know, you get delayed rejection, you get all these wonderful things. Extra chance, shadow, firefly, quantum, wormhole, Riemannian, you know, empirical, HMC, whatever. All these things are real, by the way. These are all names of samplers, like relevant names of the samplers, but you don't see them used in practice. At least I don't. Maybe I'm missing something. Maybe it's flying. You know, it's just I just didn't get it. But I don't see applications. I don't see, you know, biologists using it. I don't see social scientists using it. I don't see machine learning people using it. You know, you see them use a popular one, right? Like just standard HMC, nut sampler, they use that, and a few things. But yeah, it seems like these things are not accessible, or either not accessible or not known. Either way, it's a problem, I feel. Of course, they are of interest academically and theoretically, and maybe it is the case that unless you have superb result, the application people are not interested to learn your fancy stuff and just want something that is easy to work with. Don't know, but yeah. So yeah, it's a tiny bit strange. Tiny bit strange. If anyone's watching this stream in the future and that has a wealth of applications of these latest greatest samplers that I'm not aware of, please let me know. I am interested. Which means that it could be actually interesting to just work with application people and focus on some of these things, right? Maybe say to get, be the person to push for some of these methods to seep into molecular dynamics or physics, or I'm pretty sure there are people doing that, but either they are not doing that much, or that they are doing it in a way that is quite siloed away from this literature. So, either way, the conclusion is that it does not reach me, so either I don't read enough, possible, or that it's just not penetrative enough. What was I talking about again? Okay. Haha, look at this. Oh my god. I'm tearing. In this section we recap background material that is not easy to find gathered in an accessible format. Yes, I need this. Where's this? I mean, this is, you know, last week, but this paper is out last week, but this is a fantastic. This is gonna be an important paper for PhD students and people like myself, who are PhD students, or people just learning the subject, or people who are already researchers but trying to jump into this. Blah blah blah. I talk a lot. Okay, continuous state space. Let us read fast. Try at least to go fast. Okay. Yep. Yep. Yes. 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 Oh, wait. We will need to handle non-AC cases, but only for measures that can be described using Dirac delta. Yes. So, we'll avoid technical language. What? Okay. It is a theorem that I think any measure can be broken down into a absolutely continuous measure and a singular measure. So something like the Dirac delta. I think that's what it means. I don't know. I guess once you describe Dirac delta, and then you can form everything as a sum. Maybe. A necessary condition to be correct is invariance. Yep. Invariance is arguably the most, well, it's not the most important thing, because there are methods that are not invariant, that are biased, and people still like them because they're good. One way to ensure invariance is to use detailed balance. Yes. Okay. For AC kernels, it simply means that the two sides are equal for almost all. For non-AC kernels, two sides may not be defined for pairs of interest, and one should interpret the left and right sides as measures over the Cartesian product space. I just finished my exams today. Hey, congratulations. So wait, so you're done with your masters? Is that what you mean? So now you are a masters. Now you have a masters in law. The chat is very delayed apparently, so so I'm only seeing this quite a bit later. Nope, I have 2 more modules next May. Okay, next May. Oh, so you finish your semester kind of. Note that the operator acts from the right, the opposite convention in integral equations. Oh yeah, that's kind of strange. The opposite convention. Why? Is there any reason? Or is it important? Four modules, I completed 2. Oh, okay. Good luck. How was your paper exam? Difficult? Easy? Where am I 100 plus at? product measures, which means the weak sense for all measurable subsets. It was hard. Oh, okay, it was hard. Oh, I mean, but hard doesn't mean anything, right? As in, okay, it means that it's hard, but you could still do very well. Okay, wait, let me read this again slowly. I think I'm missing something. So the equation 3 is detailed balance. For absolutely continuous kernels, this means that we have this for almost all xy in continuous state space S. It means I can't be model answer, okay? I mean, to be the model answer, you need to be the best answer or something, right? So because it's hard, maybe you still can be the best, I don't know. For non-absolutely continuous kernels, the two sides may not be defined like infinite for pairs xy of interest, and one should interpret the left and right side once multiplied by dx dy as measures over the Cartesian product space SS. Then 3 should be interpreted as the left and right side being equal as product measures, which means the weak sense. So you instead you equate the integrals. For ease of reading, we will write statements of the form 3 about kernels over xy that represent product measure, with the understanding that they should be interpreted as 4. Okay. Finally, we recall the crucial fact that detailed balance implies invariance, which substituting 3 into 2 and then using 1. So if you substitute here into here, you cancel off, and then you use this, you are good. You can pull out one of the factors, and then you just get the other guy out. So detailed balance is sufficient, but not necessary for invariance. But if you blah blah blah. Detailed balance. Wait, what was the thing about detailed balance? For example, the estimation of effective sample size occurring using our experiments taken from 10 relies on the chain being reversible with respect. Taken from 10. Ah, so you need detailed balance. Interesting. Okay. Yes, okay, let's go on. Metropolis Hastings. Yup. Okay. Okay. A little bit uncomfortable about the fact that I don't fully appreciate the non-AC part, but okay. Yes. Yes. Yep. Yep. In the case where Q is not AC, then 6 should be taken in the sense of equality of product. Yep. If Q is AC and everywhere positive, then the standard acceptance is the most efficient choice for alpha that satisfy 6. Yep. Yes. A sketch of the proof using the weak sense would be, wait, what is stress? Using, oh yeah, okay, they're using Fubini's theorem, using one leaving the weak statement, blah. Ah, that's a good point. Yeah, that's a good point. Yeah, I mean, I know it's optimal, but I forget sometimes, yeah. With kernel Q for honest. Okay, let's keep going. Not slow down. We will finish this no matter what. Q. If the proposal to S is rejected. Yep. 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 Yes. So the point is that I don't fully remember these types of expressions, nor do I. My current understanding is that it's not terribly important to memorize these or to fully understand how they derived, because this is kind of just a result that pops up because it gets arbitrarily complicated. So I just study the case where it's a once delayed, right? The rest is like it's just gonna get stacked on each other, the definition, and get really, really messy. But this one makes sense. So, okay, wait, let me just read this one more time just to be crystal clear. So you do Q2, Q1, what's this? There's a figure. Wow, so nice. Yikes, I am going to have a hellish time to finish this, but we try. There's 3 people viewing this stream. Something's very fishy. I have my suspicions as to who they are, but I shall not name names. So wait. So you want to make a second proposal with the kernel Q. To Y if the proposal. Wait. How do you describe this again? How do you. for each x and s. So it's defined over the state space. Okay, I can do that. Okay, so this, now you want to produce y from x and s1. Yeah, q2. Yeah, the transition analogous to 5 must account for 3 possibility. The transition meaning the whole, the long, yeah, this thing must account for a couple of things. Yep. So it either ends up in state 3 ways to end up in state y: acceptance of q1, which wait. Yes, so which uses the usual MH, acceptance of the second, which come up with something new, and then for cases and the rejection of the second proposal from itself. For case 2 and 3, one must marginalize overall possible rejections of first. For cases 2 and 3, yes. Let me try to write this down without looking, see if I can get something sensible. Okay, I'm not gonna look at the answer. I'm gonna try. Let me just type it out maybe. Typewriter. Okay, so I'm gonna say that k xy is equal to q1 xy and then alpha xy plus q2 qsy. This will be qa1. So this will actually be q1 xs and then 1 minus q1 a1 xs q2 xy and then a2 xy sy, or maybe it can be xsy. Should be xsy. Whoops. xsy. Does this make sense? Make it larger maybe. How do I make it larger? So I have 1 term, 2 term, and then this would need to be integrated over S. Maybe let's put it like this. So we have 2 terms, and then the last term would be Q, the rejection. So Q1 y over S, and then 1 minus A1 ys, and then ds. This will need it to be integrated over S, then that means this will be ds2. Don't know. Does it look good? Let's check my answer. Q1, so you look at here, Q1 A1 and then Q1S 1 minus XS, Q2 XSY, A2 XSY, and then 1 minus AY and delta Y. Dude, it's so damn correct lah. It's the exact. How do you define R, however? Because the last term is slightly different, even though I think mine is sensible. It's the exact same, yo. I think me understands. Yes. Yeah, so R is just defined as Yeah, but R is just 1 minus A, right? I mean, you need a Dirac delta. You cannot have Q. It's a Dirac delta. Wait, why don't they state it? It's very weird, huh? Here, Dirac delta, fine. I mean, we can take a look. It's 11:30. I've been at it for what, more or less 2 hours tonight. Close to 2 hours, I think. 1 hour 45, something like that. Yeah, let's look at this paper here. So I think this should be stating the... Yeah, there we go. Hey, look at that, look at that. 1 minus, check that out. So it's 1 minus alpha q xu du. Then with a Dirac delta here that I forgot. And what I have, so mine would be xs and then xs. So here, see? ys, actually yeah, it's the same, because what they have here is that you can say that last term equals to same as Dirac delta y over x, and then have the same thing, q1 xs 1 minus blah blah blah. So yeah, cool, surprising. I actually understand something. Yes, the factors q1 1 minus is in the integrand are possibility of making the first proposal and rejecting it. 1 minus a1. The goal is then to choose alpha 2 such that db is satisfied. Yes. We have already established that this holds for the first term and the r square term, the r2 term. For this term, what the hell is this? The first term and the r2 term. So does it mean that if you satisfy yes, which means by 8. Yeah, so you just need the middle term. Okay. Yep, so this is the naive way. Simplest. Oops. 5. So we have detail balance no matter what. So it's trivial, yes. I should really write this down. Yeah. So if there are one, wait, if this is higher, smaller one. Okay, it's time for staring, guys. It's time for staring. Let's stare at this for a little while, okay? And figure it out. So if x if the first thing is larger, if this is larger, then we get 1. Let me write something down, otherwise I'ma forget. Okay. So alpha 2 sy equals to let's just call the whole thing h. So this is hy, hx, and then 1. Right, let's assume so this would be hx times which would be mean hy or hx, and then the other one will be mean hy or hx. I see. So divide by itself, and then you pick the minimum. Right. Make it smaller. The computer is tripping out. Hey, it's moving and I didn't do anything. Okay, give up. Okay. Note that when we propose delayed-rejection HMC in the next round, we will not be able to use this method, and we need to return to the original integral condition. Really? Huh. Yes. So this is for this integral, right? Integral. You can assume that there's a reversible map from S to S prime and apply a change of variables to identify a more generic. Interesting idea. Okay. So this, yes, it's an interesting point. Yep, unit Jacobian everywhere. Ah, I see. Okay, so when you have volume preserving, so now it's getting complicated. So initially okay, the goal is for detailed balance to hold. Late night paper reading yes. Yeah, it's just about 5 minutes for midnight here. So yeah. When I feel lazy, I make myself feel better by reading. So okay, so things are getting complicated here. So the goal is for detailed balance to be satisfied, and to get that we need to fulfill the detailed balance equation, which is pi acted on by transition k almost everywhere. And for the non-AC cases, we need to fulfill the integral, the weaker the integral case. And however, we are assuming that our proposal is random, right? That we have so you see we have Q a proposal kernel, define a normalized PDF over the states of y, and that's important, so that we can formulate everything like this. Does it make sense? Let me think. Yeah, so that means it makes sense to consider these things like this. But now I'm using a deterministic map, which means this is no longer a PDF. So it's a little nonsensical. So now we are trying to define it properly by way of a singular measure, I believe. Let pi be an absolutely continuous target density. Let f be a volume preserving involution. Then mh with deterministic proposal kernel qf given by 12, which is the Dirac map, with acceptance probability alpha. Obeying this has detailed balance with respect to pi, and therefore pi has pi as invariant density. Okay. Wait, so indeed it looks very similar. So we just need a symmetrical structure. Proposal kernel given by f. I see. Okay, that's cool. The key point is that formula 13 does not depend on function f at all, just on the ratios. We have not found this well explained in the literature. It's right. I mean, it's true because I don't understand, or rather, I didn't have this insight till now. This will allow us in the following to place HMC on a rigorous footing. Okay, what are we looking at? MH proposal, Gibbs move, M Gibbs, then MH. I mean, in some sense, I don't think this is terribly hard to understand, but the proof is a little tricky. I'll read the proof later, maybe another day. And I'll probably need to reproduce some of these things in my thesis as well, the correctness and detail balance of HMC. But I don't know how to really write these things because I would more or less be regurgitating theory that is, you know, from somewhere else. Can I just reference to it? Or should I try to write it in my own way, which I don't know what that means either, because it's theory, right? It's pretty standard. It's not new, I didn't invent this. So. Okay, that's okay. Alright, let's continue reading. Yes. Yes. Yep. Yep. Mm-hmm. Yes. This normalizing constant that we do not know, right? Yep. Ancillary fact. I have not used that word in a long time. Ancillary. Okay, I think this is an important point. So the most important part about the deterministic proposal or the deterministic map is that we have the correct invariant distribution, that it is simply anything that is volume preserving and involution and an involutive. Right, so as long as it's a volume preserving involution, again, volume preserving means that the unit determinant of your phase space, it means it doesn't change the volume of your phase space per unit, and involution just means that you can apply it twice to get back itself, right? Or rather, it is the same as it is its own inverse, yeah. Right. And I guess with some assumptions they are bijective, like this statement is a if and only if. No, not true. No, not true. Not true. So the inverse map is itself, yeah. So if we have this, then we get a correct algorithm. Correct in the sense of that it is targeting the correct invariant distribution. The fact that we are using an approximation of the Hamiltonian has nothing to do with correctness, it has to do with mixing. And I think this distinction is important, and indeed I do not read it anywhere else, or I have not read it anywhere else. I guess if you're an expert in this area, this should be an afterthought, right? This should be like, oh yeah, okay, makes sense, and it does. But it is good to see it written down clearly by an expert. However, the exact dynamics is restricted to a level set, and staying permanently will not sample correctly. This Gibbs update because preserved because Q and P factors, yeah, because the Metropolis and Gibbs are both preserved stationary, so does their composition, which may be viewed as a single update. Yeah, in particular, it doesn't do anything, right? Yeah. Yep. That is correct. Yep. Yep. What? Hold up. How do you write this? Yes. But what is P? Oh yeah. If you have not seen Mr. Robot, go watch it, by the way. Just a random shout out. But yeah, very cool series. I mean, it's ended actually a few years ago already, but it's a dope series. Okay, clearly I'm losing steam. Let us figure out a way to keep pushing. Jeez. Hey, Lamau, my paper is cited. Okay, whatever. Cool. Okay, so I think I really need to read up to maybe the rest is just examples. Up to here actually, 16 page. Where am I? Where am I? I'm at 10. Oh, I'm almost there. Okay, okay. I mean, the experiment part I believe should be quite fast to read because, you know, it's just like it's pretty much no more new information other than the results. No more new theory. Okay. Yeah. What's his name again? Okay, I am losing gas. Should I maybe motivate myself like, oh, I get to have some supper or something? But that's bad. But it's good. But it's bad. But is it? It is. It is. It is. No question about it. Oh, okay, I'm getting weird because I'm getting tired. In other news, I'm starting a new project. A continuation of my first project. It's a generalization and an extension, so I'm quite excited for that. Hoping to get some good progress in this week. Yeah. Yeah. Yeah, whether or not if I get to submit my thesis by next year January, it's still a big if. But past few months have been really productive. Actually, I learned so much, and I'm pretty glad. So whatever it is, I should keep it up and do the best that I can do. Really, not much I can try really. By the way, Twitch is not allowing me to upload my streams to YouTube. I don't know what's up with that, but so yeah, I don't know. I'll see if I can somehow work around that. But if you have not seen if you want to see past streams, it's in my YouTube account under the same username as my channel name, Column Spaces, which if you don't know is the span of columns in a matrix, which is just a terminology in linear algebra. Okay, where was I? Oh my god, because I'm looking at the 2-hour music footage. You know, I'm just looking at it. I'm just staring into it. Just staring at it. And I feel like I'm learning something. Okay, I'm not. Okay. So Gibbs sample, yes, Gibbs update and Metropolis update. Perform Metropolis update on X using a deterministic map F, where we compose operators. So P is a final operator, where L is a predetermined, L and P are defined above. What the hell is P? Is it the momentum flip? Yeah, it is momentum flip. Sneakily defined at the corner so that I can't find it. Sneaky. Okay, so you do L a number of times and you flip it, and then you approximate yes followed by P flip sketch in figure 2. So A is just your L, and then so this would be pew. Okay, yes. Okay, by now by now, you know, it's not like a boast or anything, but given my involvement in this subject for now, I should really be really good at it. If I'm not, it's a problem. I should be able to recite this in my sleep. Yep. Yes. Oh, what? Huh. Wait, why? Although steps 1 and 2 separately do, step 1 detailed balance, step 2 detailed balance. Yeah, composition do not. Huh. Oh, okay, I mean, I guess I can see that. So okay, remember that. Okay. Yeah, you can use as many as you want. Ooh, neural networks. Oh, hello, generalized HMC with neural networks. Ah, I think I read this before. It is trying to use neural network to learn the do I have this? Let me search for the paper. Do I have the paper? Generalizing. I don't. But yeah, I definitely have read this paper, I think. Let's see if I remember it. Yeah, so you parameterize the kernel by neural network. Yeah, okay. Let's not get sidetracked. Lesson. Okay, I like this paper really because it mentions a few things that are important and is targeted towards understanding. So you know what it's saying here. You know, these mentions about, oh, you don't need to be approximating the Hamiltonian dynamics, whatever, doesn't really contribute to the algorithm that they want to talk about, but it doubles as a tutorial, which is very, very valuable. And I would say that, you know, if I read this, I actually learn more which I can apply to other methods than sometimes just specific papers. I just had an idea, I don't know if it works. So instead of approximating the mass, you can approximate the variance and then do idea. Because I kind of feel like if you get the mass matrix right, you get everything right. So you're trying to learn the shape first, right? Don't know. Okay, let's keep on going. I hope whoever's watching, you're getting some inspiration that if you're getting tired, you can push a bit more. Yes. The hell's ghost? 4 ghosts. 1, 2, 3, 4. What's a 4 ghosts? We keep the Gibbs step unchanged and apply delayed rejection only to the metropolis step. Yes. Consider F1 deterministic after some time step epsilon and number of leapfrog steps, and the first acceptance remains the same as in classical. Yes, if the first with kernel, if this first proposal with kernel gets rejected, this suggests a possibility that is much less than 1, indicating a very poor approximate of the energy conservation, so that epsilon was too large. This motivates a second proposal via mapping F2, which uses a smaller epsilon. The resulting kernel, which is independent of S. Wait, what is the difference between this and DRAM? Wait, let me look for DRAM. Let me look for... I believe I wrote something about this. Delay rejection. Aha! Look! What I did 2 months ago, 3 months ago. Useful. Okay, let's see how useful it is. Wait, I thought I could have sworn there was a method where you shrink the oh, but it is under the Metropolis Hasting idea. The covariance of the first proposal follows any update, no damage. Yeah, exactly. So okay, yeah. So the idea is actually very similar, right? The idea is very, very similar. I'm surprised that... Okay. But why isn't it obvious that it is mentioned that it's the same as the Hario? Very similar, right? No? I'm confused. Oh. Which is independent of S. Injective. What? Injective? What's F1? Oh, injective? Injective means one to many, right? Oh, okay, yeah. Okay. So we need to compute the goal state. So it is saying that if I so F2 is simply F1 with a smaller epsilon, right? Okay, this is getting really tiring. Yes. So it is saying that, but why do you need this? But wait, I'm confused. Because F2 is irrelevant, the kernel. Ah, yes, I see. Wait, I'm a bit confused. Yeah, I think the diagram would actually help. So it's saying from here to here is too big, so you do from here to here. Which makes sense, you need to compute from here to here, here to here, but why do you need from here to here to here? Oh, do you need? No, but you don't, right? Because let me try to make sense of this first. Alpha 1. So this is F2, and then you need F2, F1. F1, F2, yes. The ghost state. This means that you move smaller, then from this you move the bigger one. That is strange. Okay. Ah, I see. The target density at the ghost. So you need 1, 2, 3. What is it, 4 ghosts? Ah, yeah, because that, right? I see. Okay, this is important. This is very, very important, because if you need to calculate so many ghost states, then it's gonna get expensive. So because okay, this is a bit confusing for me. Let me try to write it down. So I'm saying that I go from here to here. So alpha 1 because you have this broken structure. But if you have something like this, wait, I'm not understanding this right. So this is saying that I have you start from Q prime, then you have Q double prime, which is another one starting from Q, and then you need F1 F2. which means you need to move L after moving L in. Okay, so in the RHMC formulation, okay, it would be yes, and you need this, let's call it triple. That means from here Q, you go to Q1, then go to Q2, and you need to go from Q1 to Q3. So here similarly, we are saying that we move to Q1, Q2, I mean, there's two ways to get there, I guess. You can think about it like that. And this is saying that I need to compute the probability as if I would propose that as the first state. That means I will need a Q3 to go here, or to go here. This is not very straightforward at all. I'm understanding this part perfectly. I'm just thinking about how it relates to my project. Maybe I should formulate it myself. But it does look super similar though. Oh no, I think it's correct. I think it's correct because you have the negative. So I feel like you have a negative here. So these two don't do anything. Okay, maybe I need to do this tomorrow. Yeah, okay, I'm convinced that it's correct though. I mean, I feel that it's correct. Let me write my to-do list. The acceptance problem. So this is higher order. I'm not gonna read it because it will take too long to follow every single step, but I get the idea. Yeah. So you must reject everything else before that. Yeah. Okay. Yeah, every time you increase another factor of n. Oh, that's not true. It gets more and more expensive actually, because now you compute. So you have to pick A, right? Oh yeah, yeah, also of the ghost. this apparent exponential growth in cost. Constant factor. It's a bit unbelievable. I'm confused. So it's saying that, huh? So it's saying we at least need a to the k minus 2 times 6. Let k be the smallest integer such that e divided by k minus 1 gives a stable leapfrog integration. Then even for this stability, yeah, and even for this optimal step size, we need at least, so you need what? You need NE divided by E a k negative 2, so a k negative, wait, what is this? At least is it negative k negative 1? It doesn't really matter, I guess. So a is the factor, n is the number of steps. Yes. Why is it AK? The cost. Wait. So it's only AK more, and then if you divide by this, it would be just A. What? That's so trippy. Oh. Strong proposal that makes it less safe. Ah. Ay. So this is saying that if it's interesting. I don't understand. But what is this? Oh, okay, I see what you mean. Yeah, so you're saying if you reject with a high, then you don't really make it. Ah, okay. Okay, that makes sense. Right, so if HMC is effective, we don't really care about it that much. This is actually a really cute idea, a really nice idea. Yeah, I see. So this trades off. Huh. Very interesting. What do they call this? Probabilistic delay rejection? Make k minus 1 subsequent. th percentile followed by nuts. You choose time to be the 90th percentile of the trajectories. Followed by nuts. What does that mean? We choose time of the integration t to be the 90th percentile of the trajectory followed by nuts. What does that mean? I have the Wu paper, right? It's this one. What do you mean? percentile. Does it mean every time you run nuts and then you change? No, right? You just... What does that even mean? That means you get all the integration time. During the warm-up phase. Ah, so you run nuts during warm-up. Following, we choose the time. Wait, is the different paper that I'm thinking about? Yeah. Does not have jitter. Jitter. Wait. Am I tripping? Why am I not getting the same thing? Exact same paper, right? K. I don't know what it means really. So the schedule is one idea, right? I mean, Okay, I think I can get the main idea. I'll read this another time. In terms of the result. But I do want to know how. Okay, I'm almost there. Let's not give up now. We're close. Let's not give up now. This is where we get stuck. Or rejected because they are too small. That means you accept the most second and third. First one not so much. That means in this region it's very hard, then you accept, but then over you get better results. Okay. Kolmogorov-Smirnov test to check that we are indeed sampling from the correct distribution. It's a good point actually. What am I looking at? So triangle is 10 one try and then 2 try. So this is lower is better. HMC. I don't know what I'm looking at. I'm getting tired, obviously. Cost. I see. So this is cost. Strapping over the chains, right. Alright, cool. I think we're done. I have not read fully the experiments, but it seems like the overall message is that the method is good. It works for some examples, even though I have some concerns about the cost. I mean, it's a constant factor, but I wonder what factor that is, and I guess it highly depends on the problem. Not so sure. But anyway, so just to give a summary, the main method works in this way. Okay, so you make your proposal. If it's rejected, you make another proposal aiming at, with the same integration length, with a smaller step size. This means you need to compute more steps, right? So if you shrink it by 2, you need to compute twice the number of steps to get to the same overall distance. So this idea is that you hopefully better approximate your Hamiltonian, meaning to say your acceptance is closer to 1. And that's basically how the method works. And you can augment it with a probabilistic delayed rejection, meaning to say that you only you set that you only do the second retry with a probability 1 minus your first acceptance rate. This means to say that if your acceptance rate is very high and you reject, so let's say it's 90% and you somehow reject it, there's still a 10% chance they reject it, then you only run the retry at a 10% chance, right? So if you reject at a very high percentage, meaning to say if your acceptance is only 10, meaning you're at a very bad region where you really need to reduce your step size, then you will run your second try with a 90% chance, which makes a lot of sense. So a lot of things can be changed, I believe. So obviously the schedule at which it decreases the step size, maybe halving each time is too much. Maybe you can go slower. I don't know, you can do many things. And also that obviously that the heuristic choice for the probabilistic delayed rejection need not be that way. And of course this is just one of many delayed rejection proposals. So okay, cool. I'm glad I read this paper. It's very informative. I learned a lot today. Very happy that I've done so. I do have some of the questions I need clarifying, but I think that is for another day. So for example, I want to formulate or figure out how does the reflected HMC fit into this framework, just in terms of the delayed rejection part about the optimal. So it mentions that it needs a ghost pre-image that is extra computation that I don't see occurring in reflected HMC, which is suspicious because either it means that the ghost image has been computed already, which I think it has because it has that involution property that I suspect that it cancels out 2 of the operators. I'm not sure. I have to check it tomorrow. And if not, that means to say if we compute a little more things, maybe we can get the optimal, the most efficient acceptance rate. I highly doubt that's the case, but I'm looking to find out for myself that indeed the ghost pre-image has been computed in some way. Okay. Alright, cool. Yeah, I'll continue this another day. Thanks for tuning in.